So this is the talk I am going to share about our research work on Meshfree methods. Myself, Keshav Malagi, and we have a team which has been working on this for quite a significant amount of time now, beginning from 1989, in fact. So I continue the legacy of the same research group. Our main person is Professor S. M. Deshpande. He was a faculty in aerospace department in Indian Institute of Science. So he drove this research primarily. And at NAL, I am sharing my work with my colleagues Dr. V. Ramesh, there's Niranjanan, and Shikhar Jaiswal at the CSIR's NAL's Computational and Theoretical Fluid Dynamics Division. Okay. So my objective of this talk would be to get you interested in the mesh-free methods, to know what is and what are the possible research directions that one can take up on. That would be the objective that I have set out to, because generally most of you are aware of the mesh-based methods, finite volume methods, finite element methods, and typically mesh-free method or meshless method is not that much well known to the general user community. So uh, so this is the outline. I will, even though 1 week course has been going on about CFD, I presume that lot has been talked about CFD. So I will not spend much time, but I will highlight why the CFD is so complex. What is its nature? What makes it so complex? So just a couple of slides on that. And then because we have been developing codes and working on numerical methods, I'll be presenting something related to the numerical schemes. So what constitutes a good scheme? So what should you look at? So I'm sure you have heard of some talks by commercial codes and others. We have introduced you to the use of CFD. What I'm talking is how to write those codes. So both are an important aspect in the CFD. Even though you use commercial codes, it is very essential that you know these things so that you can make use of the code correctly. And then various numerical schemes I will present. This is to make you aware of how mesh-free method is different from the mesh-based methods. So before I introduce meshless methods, I will introduce you to other methods in a very brief way so that you can appreciate the differences between the two methods and understand why this particular method is required and what are its strengths and weaknesses. So in that I will share the features and different measuring methods and one particular method that we have been working on, its theory and its application to Euler equations and the associated mathematical properties and its development. And if possible, I will also try to cover the boundary conditions. In the kinetic framework and the measuring method, they come in a very novel way and very interesting. And at the end of talk, even though it is not directly related to measuring methods, but those who want to pursue a career in CFD, I would like to just briefly introduce the new exciting things that are existing. It is easy to get lost with these commercial codes and think that all the research has been done and nothing much is left to do. So I will just briefly give you a hint as to what are possible directions. So is it audible to everybody? Is it going on well?
Yes, sir.
Is audible, sir.
Yeah. So I'll continue. So what is CFD? CFD, as you have heard by numerical discretization techniques, which have been talked on earlier, or Professor Balakrishnan's talk, that it consists mainly of numerically solving PDE plus BC. So you solve a partial differential equation subject to certain boundary conditions on computers on a grid of points. This is a very broad definition of CFD. Of course, you know why we go for numerical solution. And then what does this require? It requires a computational domain in which you discretize it by many points, and various methods are used to solve the PDE. And of course, you require a computer program which has put this numerical method into a code. And once you run the code, you will generate a lot of data. So you should know how to analyze that data and how to use that data in the design. And once you generate a data, a very important thing is to know what is verification and validation. So what is verification and validation? So verification and validation in a nutshell is you will write a code and generate a result. So you need to know two things very essentially. One is verification aspect involves whether I am solving correctly. So you have chosen a mathematical model, you have written the code and you are solving. So the question you ask is whether the code I have written, the numerical method I have coded, is it right? Is it functioning correctly? That is called verification, whether what I am solving is correct. So second part is validation. Validation involves whether I am solving the correct problem. That is, you are solving a problem by using a model, either Euler equation or potential equation or Navier-Stokes equation. You should know whether this mathematical model represents the physical reality. So the question is, am I solving the right problem? So the difference between verification and validation is this. In verification, you know whether I am solving correctly. Validation, you will know, am I solving the correct thing? So these two things you should be very clear whenever you have written a code. Of course, when you are using a commercial code, you won't face these problems. But what you generally face there is whatever the process you have adopted, the methodology you have adopted is right or wrong. So to that extent, you will have to do some validation before you begin on solving a problem. So why these problems of CFD are so complex? There are complexities of geometry, that is the body on which you want to solve the, just a minute. There are there is a complex body in which you want to solve the problem. The typical things are like you will begin with a flat plate problem or something, but eventually you have to solve something like turbo machinery blades, turbo machinery full stack, or the full aircraft configuration loaded with stores. And many times some of these geometries may involve relative motion also. So you will have to deal with moving bodies. So all that you will have to handle this geometrical complexity. And what is the physical complexity? Physical complexity is you will have studied in fluid dynamics about separation, turbulence, unsteadiness of flow, rapid changes of chemical reaction, two-phase flow, particulate matter, and all such things. So these complex phenomena require you to choose the right model to solve the problem. Okay. So and then there are coupling complexities. So right now you may be, most of you will be aware that now we not just solve CFD, we will be solving structural dynamics, electromagnetics, control problems, fluid interaction. So when many of these systems interact with each other, there will be a coupling complexity because the nature of each of these systems can be different from each other, and then they have to interact. So you will have to satisfy the uh, aspects of both the systems. So it will present in itself a coupling complexity. Okay. So the same thing which I said is represented pictorially here, because pictorial is always one which carries impression quickly. You can see that the CFD has these three dimensions to it. One is the geometric complexity, as I mentioned. You can see, you can start with 2D shapes, multi-element airfoil, simple 3D shapes, core body wings and fins, core body wings, tunnels, deflected fins. So it keeps on increasing the geometric complexity. How good you want to model it. Similarly, you will see the model, that mathematical model that you want to solve. So you will have studied that many of the problems can be represented by just potential flow and nonlinear full potential flow, Euler equations, Navier-Stokes equation. They all these represent an increment in the complexity of the underlying mathematical model. The more the physics becomes starts in more and more rich. So you'll have to, your mathematical model have to account for all those things. So you can have RANS, LES, DNS, and it continues like that. Okay. And then the third axis is this coupling. So you have CFD here, then you have fluid structure interaction, then you can have electronics also interacting with it. Then you can have, this is called aeroelasticity, then aeroelasticity with stealth, aeroservoelasticity with stealth. So all such issues come up. And now in the modern times, one more axis has been added to this figure, that is the hardware complexity. Initially, you had only simple desktops or computers on which you could code and run, and some parallel machines came by later. But now, the parallel computing environment itself has become so complex, and the programming models that have come by, the languages that have come by, the hardware which is changing, these are also present a complexity in its own. So you will have to grapple with that also, so that you can use the latest hardware very efficiently. So this is what we will be solving in the CFD typically. Euler equations, which you have, most of you will be very well aware of, a conserved quantity U and the flux is FGH represented by the things, and you can see that is a nonlinear PD, okay, and it is a vector conservation law, non-linear vector conservation laws, PDs. And when once you want to include the viscous effects, you have to solve the Navier-Stokes equation where the viscous flux vectors appear, which will contain second derivatives of the various variables. So these two equations, you can see that we have the model of this physical reality. So it represents certain mathematical characteristics. Once you have a PDE, it will have certain mathematical characteristics. So those mathematical characteristics, how we can map them to physical significance. So these kind of thing helps you in validation. So in validation, you want to know whether you are solving the right model, right? So you should know which mathematical character has to be satisfied to capture which particular physical aspect. So this in nutshell tells you the kind of correlation between the one-to-one map between them. So in the mathematical characteristics, if you look at divergence form, so once you write any PD in the divergence form, it means it is in the conservation form. So you will the corresponding property to divergence form is mass, momentum, and energy are conserved. And then invariance under rotational group. What do you mean by invariance under rotational group? That is, you to tell in a very layman's language, you solve those equations in whichever rotated frame, the physics does not change. Whether you solve in XY frame, whether you solve in polar coordinates, or whether you solve in some rather than usual XY, some rotated frame, the physics would remain same, right? It doesn't change on how what frame we choose. Okay, so that is the significance of it. So your scheme should satisfy a rotational group. So if it satisfies its rotational group, it will capture the physics correctly without depending on directionality. And further, it is popularly said that Euler equations are hyperbolic. What does it mean? Euler equations are hyperbolic means we definitely know from our experiments and all that the fluid dynamics phenomena involve wave propagation. So it corresponds to that. Non-linear means you will have shock waves, right? So you have shocks where these waves which are propagated, they steepen and they make a discontinuity, which are called shocks. And then you will have ABC. ABC are the Jacobian matrices which appear when you write the Navier-Stokes equation or the Euler equations. So you write dou u by dou g by dou x when it is written dou g by dou u into dou u by dou x. So that dou g by dou u, the flux derivative with respect to conserved variables, those are the ABC corresponding to x, y, z. What does it mean by non-commutivity there? Non-commutivity means they do not have any preferred direction. If it were commuting, we can reduce it to some direction along which we can solve it. But since they do not commute, we cannot have the same directions for all. So it has multi-directional wave propagation. That is the quality when you say it does not commute. And then Euler equations admit weak solutions. That is the gas dynamic shocks. So you have gas dynamic shocks which can be seen even in the Euler equations, which does not involve viscosity, but it will show up as gas dynamic shocks. I hope this particular slide tells you about one-to-one correspondence between PDEs and the relevant physics you want to look at. And then once you have these mathematical properties, these physical realities, and you want to solve these PDEs, you will have to develop a numerical scheme. So if you have to develop a numerical scheme, you should know what is that numerical scheme should have in it. So what I have listed here is two kinds of desirable properties. One is the classical. What I mean by classical is these have been the requirements of a numerical scheme for a very long time since the beginning of CFD. And then I have put something as modern, that is new ones, which are to do with present times. So subject has evolved very much since its start in late 70s and 80s. So the new requirements have also come. So this classification helps you to know from a timeline perspective how CFD has evolved also. So as I said, conservation is an important aspect which is reflected in both mathematical and the physical reality. So your numerical method must be conservative. must be accurate. This, of course, is easy to understand, but in terms of mathematical aspect, the formal order of accuracy should be high. That is what it means when you say accurate. And large bandwidth of scale resolution. Once you are solving on a projected method, that is, you are now using a discrete approximation to a continuous phenomena. So you will filter out some scales of flow and some frequencies and waves in the so whatever you filter out should not really matter to the solution. So whatever you capture should be very large bandwidth so that you leave out very minimal. So your bandwidth should include small scale to large scale. That is what it means by large bandwidth. And rapidly converging, of course, the solution, if you write a code or numerical scheme, it should converge very fast. That is, you should get solution very quickly. It should not happen that I give solution now and yeah, I give a run now and I get solution after 10 years, because it will take that many number of iterations to converge. It should not happen that way. Very realistic times, it should converge very fast. And because there are so many approximations are involved, higher order accuracies is involved, there will be oscillations because of numerical artifacts. And such numerical artifacts should not appear in the solution. So your numerical scheme should be such that it should not lead to these spurious oscillations. You should take care of that. And then positivity preserving. What I mean by positivity preserving is, if you look at the physical problem, that pressure or temperature never go to negative, right? So such things should be reflected in your numerical schemes. That is, quantities which do not become negative at all in the nature should not become negative in the numerical scheme. It should have, that is called positivity preserving, in the sense of pressure not going negative or the temperature not being negative. Okay. And then because these PDEs involve certain symmetry properties, one of the symmetry properties I showed was this rotational invariance. So they should preserve such properties. Okay. And then because these codes have to be run on large machines, the data on which the numerical scheme depends should be very local, that is very immediate neighbors. If you want to do an approximation at a given point, it should depend on very immediate neighbors, so that there is very less communication between the processes. Should be robust. Should be robust means for any given kind of geometry or very bad grade, the code should be able to run and produce valid solution. That is what is called robust. That is, code should not blow up. Typically, you will see in CFD sometimes the solutions don't converge, or you get some very spurious and wrong solution. So such things should not happen. The code should run and generate valid solution. Should be robust. Entropy condition satisfying. Of course, as mechanical engineers, you will know that only those solutions which satisfy entropy are genuine solutions. So your numerical scheme should always converge to solutions which are satisfying entropy conditions. So these are the modern things. So the modern thing is, these codes or numerical schemes should not only be working on very nice, good structured grid, they should also be working on unstructured messages which are hybrid in nature. That is, various kinds of elements are mixed. And higher order schemes are required now, more than two. What you mean by higher order scheme is, until now was used to be two. So people are now looking at third order, fourth order, fifth order schemes, so that you capture the flow with minimal number of grid points. Low dissipation and dispersion, that is, it should be, when you are dealing with flows like vorticity dominated flows, the scheme should be very less dissipative, so that you capture the transport of vorticity, and dispersion should be less because it should not be distorted. And then these kind of schemes should have very F by B ratio. F by B ratio here means floating points to byte ratio. That is, the floating point represents the computation part, byte represents the data transfer between processes part. So if you have high computation per data transfer, then it will be very good to use the latest hardware. So, and you should be able to use whatever the vendor has provided, the primitives, because they will be optimized on that platform. Your scheme should be able to use such new modern things in the available hardware to make the code run very fast. Minimal internode communication, as I said, the byte, the data transfer between processes when you are running on large machine should be very minimal. And once you are using a large machine, you typically split your grid into various small grids, and each small grid is assigned to a node of the computer. Then it is solved there. So this thing is called domain decomposition. So you will have to do partitioning of the whole grid, which is then assigned to each processes. In the, once you are running on a big parallel machine, if you have to do this partitioning repeatedly, which is called dynamic repartitioning, it should not be called frequently because it will take a lot of time, and that is not the computing part. It is only data transfer part. So so it will delay your time to get the solutions. So now I covered these numerical schemes. So I will just briefly highlight because you will. I saw in the brochure that other people have covered the discretization techniques and all. So I am not going to go full details into it, but just will highlight only that much which is necessary for you to appreciate Meshfree methods. So there are these various finite difference method, finite volume method, finite element method, spectral method, and of course Meshfree method, about which I will be talking little more detail. And then this lattice Boltzmann method. So I will introduce you to just the basic necessary that is needed to understand the Meshfree method. So finite difference method, there are various examples you will have heard. These were the schemes which began in very long back. Lax-Ventropf method was one, McCormack predictor corrector method was one, then upwind based differencing method started, then central differencing with some numerical diffusion were also looked at. So what do we do here? Here we solve the PDEs on regular meshes, and it is solved in the differential form. And at each point we try to drive this residue. We call this residue whatever is the flux for a steady case to zero. So it converges in this sense. So important to know, it is a differential form which is used, and it is the max Rijk which is the convergence criteria. And then finite volume methods. So these are the flux vector splitting method, flux difference splitting method. You will have heard Van Leer splitting, Van Leer flux splitting method, Rose flux difference splitting method, and of course Jameson's method of adding artificial diffusion. So what are the features of this in this compared to finite difference? Here we solve the integral form of conservation laws. And this you can solve on arbitrary meshes. Where a finite difference we had to rely on a nice structured mesh. Finite volume can handle the arbitrary meshes. And convergence here is in weak sense, that is in the integrals. So you have a typical mathematical property which says it is a weak convergence. These are very popular in engineering community because we can handle more complicated geometries using this in a very easier way compared to finite difference method. And of course, many of our Indian aerospace codes are based on this FEM. So this is typically of what you can see as a cell-centered finite volume method. These are various cells, and this is a cell vortex method in which you solve at this cell vortex and find a dual volume here. Okay, and various kinds of elements, quadrilateral and hexahedral prisms are all can be merged and used. So as I said, integral form is used. I'll skip these details because you will have been taught it. Just this thing, if you want to solve in this element P, you will have to sum up the flux at all these three sides of it. So if you want to flux at this phase, it will be a combination of flux at this interpolated here and flux here interpolated here. So that is what is given, the plus flux and minus flux, the upwinding properties. So basic state update will be like this. The new state will depend on the old state minus this correction because of the fluxes. So what you realize is you require a mesh and a lot of properties of mesh. That is, surface is required, surface normal is required, the area is required. Once you go to 3D, your volume is required, and each the 3D surface there, you have to deal with all this uh, mesh complexity handling. That is, mesh has its own geometry which you have to handle. And finite element methods are also popular in CFD. Some of the people have been using, and these are the typical uh, two of the examples I have given here. I will not go detail into these finite element methods, but suffice it to say that here differential conservation form of conservation law is used But here also weak convergence is used. So these are the two things you should know about finite element method. That is weak convergence, and then a differential form is used. Here also you will need to define elements which are like what you saw in finite volume, surfaces, the element size, their in relation to the neighboring, all those things are needed. Spectral methods, of course, are based on Chebyshev polynomials or legendary polynomials. These are typically more popular in the weather modeling, where they use these for like meteorology and all those things. Because the boundaries are simple, you can use such things. Where boundaries are not simple, it is not easy to use these methods. So given that I have talked about all these methods now, you appreciate that they require some kind of grid, and that grid is also required to be handled geometrically. So if you have a very complex geometry, the first job of you will be to first generate a very good quality grid. I'm sure you have heard of the grid generation aspect in few of the lectures in last week, and you appreciate some aspects of how much time and effort and all is required to generate a mesh, good quality mesh. So compared to that, in the meshless methods, we do not need a mesh, but that doesn't mean that we don't use any points. So what it means is we don't use mesh, but we require still some finite number of points on which you have to solve. But only thing is the way we generate these points is very flexible, and the requirements on that are very minimal. And I will introduce you to these meshless methods now. First, I will cover their basic features and why they are required, and then the mathematical nature, mathematical model that is used to all the solve the problems. Okay. Some of the just 1 minute. Excuse me. Sorry. So some people call them as finite point methods also, because you have only finite number of points on which you are going to solve the equation. So there is no cell or element. So they like finite volume method is called. They want to call finite point method. So one of the examples which started way long back in smooth particle hydrodynamics. This was used for astrodynamic simulations majorly. So one of the things in the smooth particle hydrodynamics, it was used for exploding stars and dust clouds. So way away from our usual aerospace CFD, but it is a similar numerical method. And what I am going to talk mostly will be about telescope. This has been developed by Professor Deshpande and his students in our community, and I'll give examples of that. And LSCOM is least squares kinetic upwind method. So it is briefly called as LSCOM. So what are the features of this meshless method? It works on any cloud of points. That is, you want to solve the PDEs at any given point, you just surround it with few points, you can solve it. So solution at any point is approximated by values at the nodes. So you have a body and you fill all the domain around it with some points, and you can approximate the solution at each of those grid points. At each point in the connective point in the cloud, its neighborhood information is required, which is called connectivity. What is connectivity? Connectivity is if at a point Pj is where you want to solve, you should know who are its neighbors within the distance of Pj to Pi. All the I neighbors which are having within the distance epsilon. So some length scale you take within the connectivity. So the closest neighbors is all that you should understand. So the closest neighbors to that point, that information you should have, and at each point you approximated you will be available. Then you can solve the PDE on that. So one of the major problem in the meshless methods would be just generating this connectivity. So given a point, who are its neighbors is a thing which you have to be ready with before you solve the PDE. So since it is only a collection of points, we keep calling it as cloud of points. So it will make it very clear here. If this is the whole domain, the whole blue color that is represented, is the whole domain, and you want to solve PDE at all the points that are represented by black. So sigma is domain, and I, J, K are typical subdomains. That is, you want to solve at this point, you want to solve at this point, you want to solve at this point. So if you want to solve at this point, this is its neighborhood. So you want to solve around this. So this is its connectivity. So the yellow part is connectivity for J. So this cyan color is the connectivity for I. Similarly, this brown color is for K. So you will have this connectivity. So these one thing which you should very clearly see here is in the finite difference or finite volume methods, once you are solving at any given point, you were considering the other points, but there was never overlap of any cells. That is, you want to consider a cell, your neighboring cell will be considered. But here you see, you want to solve here, the points that are used to solve here are overlapping with this. It forms a overlapping cover, it is as it is called. Okay, a little more detail of the same thing. So you have this typical mesh or grid in the mesh based method. So you will have an say aerofoil, you develop this unstructured grid around it. So you will need all these surfaces, these all things have to be defined. Whereas in meshless methods, you have just a typical point cloud. If you have an airfoil, you surround it with all the points of cloud of points, then you can solve on it. So what does it mean? What will it result into in terms of our effort for solving a problem? I'll demonstrate this with a problem where there are two airfoils in the domain. Suppose there are this red and green are two airfoils. If you have to generate a grid, you have to generate a grid around two airfoils and a domain, considering all of that at once, either unstructured or structured, multi-block structured, you have to use. But whereas in the mesh-free method, what we can do is generate a grid. You freely use grid generations, but in a very simple manner and without constraining them to satisfy all the properties that are required for a finite volume. So you use the existing grid generators in a very efficient and easy manner to generate quick grids. So and without worrying much about the quality of the grid. So you generate a grid around each airfoil and you separately generate this. You separately generate. There is no need to worry about each one. Each component, like whole domain, you generate one cloud. This each airfoil you generate one cloud, and then you merge all the point clouds and then take out those which have entered into the body. Like if this red would have entered into the body of this green airfoil, so you delete, but only consider only those red points. Like that, whole domain will have points which are lying inside these two airfoils. You blank them out. So at the end, you will have a cloud of points which is formed by grids around very simple geometries which can be generated extremely fast without worrying about quality issues. And also, you can generate very high quality point clouds because there is a flexibility in how you generate the point clouds. For example, you take the case of airfoil. In this airfoil, you generate a Cartesian grid to fill the whole volume. And near the body, where you want to resolve the body very fine, you generate near the body a structured grid. You use the point clouds obtained from a structured cloud. And because at the trailing edge, you know that the polar grid is always good, you use polar grid. And now you merge various kinds of these grids to obtain a point cloud. These kind of things are very unthinkable or very difficult to do in other methods. Here you can mix and match any kind of thing and obtain a kind of discretization which is very much suited to your problem that you want to have solve. So typically you will know point cloud is a distribution of points around the object in the flow domain, and connectivity is a set of neighboring points given a point. So if you want to point and this the neighboring points, you should know. Okay. So you can generate a point cloud by generating grids around each individual clouds. You can call them as point clouds around each individual geometry and then merging form a large cloud. So I will put them in words whatever I said now. So all these point clouds are not connected by grid lines or coordinate surfaces, and they don't form any tetrahedra, hexahedra or prism. It is just a point distribution. You can use any kind of Cartesian cloud, quadri cloud, chimera cloud, or even advanced inference method and generate a collection of points on which you want to solve the PDE. And once you know that there are no prisms or any elements or things, you can easily visualize that if you want to do adaptation, that is, what is adaptation? Adaptation is you want to increase the resolution in some areas where you feel physics is more dominant. That is, there are more physical features. You want to have more resolution of the space discretization there more. So you want to put more number of approximation, finer approximation. So you have to put more number of points. So it is very easy because wherever you want, you can put just go there and put more points. You don't have to worry about its neighboring and other things. You just increase the point density there. This aspect is very difficult in finite volume and finite difference method. You will have to worry about the resulting grid that appears because of finer resolution that you want to do locally, because it affects all the neighboring points. You have to recalculate their volumes, recalculate their surfaces, everything. But here it is not that. And of course, the unstructuredness of the point remains the same after the enrichment. And geometrically complex configuration, you can divide them into simple configuration. Like if, for example, you take a full aircraft configuration, you can easily generate a complex just a grid around point cloud around the fuselage, a point cloud around the wing, a point cloud around the tail surfaces of the wing, the elevators, ailerons, rudders, and then merge them to form a full point cloud on which you can solve the full aircraft. So you can do this in just a few minutes of time compared to hours of time that we typically require to generate good quality grids. They are called chimera clouds. In the finite volume, they call them as chimera grids, where they have to worry about overlap, the solution transfer from each grid to other. Here we call chimera cloud, but there is no worrying about transfer of data between the various kinds of point clouds. So the whole idea is you quickly generate a cloud of points, and all the burden is taken by grid-free solver to solve on the structureless point cloud and obtain the numerical solution. So just some examples of various point clouds. So this is called a simple point cloud where you can obtain the point clouds from an unstructured grid. If you have a structured grid, you can obtain the point cloud from there. You can see that around airfoil both have been represented here. You don't need the information about their cells, their how do they connect to each other and all such information. You just need points from there. Similarly, these are called chimera clouds where multiple grids are overlapped and you obtain a point cloud using that. So you can also use the embedded Cartesian meshes, that is one inside the other, or various point cloud distributions using Cartesian. These are very fast to generate. These can be generated in a minute's time actually on even pretty complex configurations. So you can see I have put this picture. This is a borrowed picture to essentially show how such a complex geometry on which if you have to generate a grid for finite volume or the finite difference or structured grid will be very difficult. Whereas, so finite volume people typically go to these either multi-block structured grids or unstructured grids with a variety of hybrid elements. But in Meshfree method, you can see that you can generate good quality simple grids around each of these components and merge them to form this whole point cloud. Further, you can see the same for a full aircraft configuration I have shown. So for this full aircraft configuration, this is M16 configuration. It is called FAME mesh. That is feature associated mesh embedding. As I said, you can generate a mesh around fuselage separately, wing around separately, canard separately. Such a thing was followed, and it was only the mesh-free solver which could solve on such a distribution actually. And this meshless adaptation, as I said, is so easy. You can see that we begin with this first level, and after 7 level, various colors of point. What you see dots there are the point density is increased there without worrying about grid. So you begin with this point cloud, you go on adding the points around the features, around the places where there are features. Here in the initial solution, you can see that this is a Onera wing and there is a shock, lambda shock formed here. So you go on adding the points and you will get a very sharp featured shock. So this is the adapted cloud. And this is so easy because you just keep on adding the points where you want. And once you have the further advantage of mesh-free methods is once you have these moving boundary problems. Suppose there is a store moving away from the aircraft. That is, you have an aircraft and some store is moving, falling from here to the down. So you will have moving body problems or turbo machinery problems where they flutter problems, where there are moving components. You have to handle those. So once there are moving components in mesh-based methods, you will have to manage the mesh as the body moves. So you will have typically like this is what is used in finite volume methods in camera based finite volume methods. You will have two kinds of grids, one grid which moves with the moving body, other stationary, and these two grids are overlapping. Now you have to worry about at any given point P, if you want to know the solution, once you solve you have to also worry about the what is the overlap with the other mesh, and then there has to be solution interchange between these two overlapping meshes corresponding to their ratios. And also satisfying conservation on such overlapped meshes is a challenging task in finite volume. Of course, very efficient methods have been evolved, but it is a very involved process and very time consuming one at that. Otherwise, you will have to go for full regridding as the body keeps moving. But look at the advantage when you have a mesh-free method. So you have a grid around the aircraft and then a grid around the store. Okay. So whatever is grid around this aircraft, in which we remove whatever is the grid points have from this have entered into. Similarly, from whatever grid points from this point clouds from this have entered into this aircraft, we remove that. Blanking points lying in and around store. So in this aircraft, we delete whatever the points that have entered into this store. Similarly, whatever points that have entered into aircraft are removed. Now you merge the both, you will obtain a point cloud in which you have aircraft plus store. Now you solve on that. Suppose the body moves to a new position, you redo this step. Then you redo these steps, which takes order of few seconds actually, and you can compute the body. So you don't have to worry about these issues. Also, one has to realize when we do these kind of things, we end up doing a lot of interpolation, and that interpolation does not necessarily satisfy the PDEs which we are going to solve. So the solution that we obtain is not necessarily one which has satisfied PDEs completely. Whereas here we take it head on. We solve the PDEs exactly accurately at that point. Not exactly, but of course, it's a numerical method. So, but we do not have any approximation in terms of solving that. Like interpolation errors and others are not involved once we solve these things. So same thing is here. So as you saw, now I'm sure you will appreciate these points which I'm going to make, which have been now illustrated through pictures in the previous slides. So why this mesh-free method is required? So you have to have mesh is a prerequisite if you want to use FDAM, FVM or FEM. And you also have to worry about grid topologies, what kind of grids you are going to use, what is the accuracy because of that, and all such things. And mesh generation is a lot of work, and the automation is much less there compared to what we can achieve in the point clouds. That is, there is no human intervention in generating the point clouds compared to the mesh-based methods where there is a lot of human intervention. Okay, and it is easier to generate these around simple geometries and merge them and make a huge grid around a complex body. Okay, and once there are problems where there are stage separation, vibrating blades, all these where there are moving boundaries, it is very easy to manage with these meshless methods. And also when there are time dependent camera clouds, that is as the body moves, you will have these overlapping meshes as I said about the store separation, that aircraft plus store I said, that is one of example of time dependent camera cloud. So you can see that it is pretty easy to handle with this. Excuse me. So having said about all these features of measuring methods, why they are required, what is their advantage, I would briefly tell you about varieties of measuring methods that have gone on. Even though so many Meshfree methods have come by and have been used, I think the LSCOM has been far more successful in solving the large number of application problems. That is one advantage with our group, that we have managed to solve uh, huge applications which are very relevant to engineering issues. Okay. So as I said, it starts with smooth particle hydrodynamics, and then these generalized finite differences of Liska and Orkis, and then our own LSCOM, least squares kinetic upwind method, starting developing in 1988 and so on. And then kernel particle method. There are other in the structures also, element-free Galerkian methods, finite point method has been used for both. And then MLPG, the meshless local petrogalerkin methods, point interpolation method, point assembly method. And then one more method which is derived similarly from LSCOM is the least squares finite difference method. Least squares finite difference method developed by Balakrishnan. So now I will briefly go through the LSCOM Meshfree method, which I am going to tell you, which is my area of research primarily. A brief background before we actually begin LSCOM. How did we start working on this problem? Why the Meshfree method was looked at was to have certain feel for what was there in 1980s and so. India at that time did not have access to good quality grid generators, or commercial grid generators which are available now were not easily available then. Lot of them had also export restrictions from the countries of origin. At that time, you could not get many of these technologies easily. Even though today you get a lot of these commercial solvers, grid generators so easily, at that time our ability to solve CFD problems was greatly limited by availability of grid generators. It was a big hindrance. So Professor Deshpande at that time thought, why not think of a method which minimizes our dependence on this mesh generation. That is how the idea of this LSCOM was born, and the first publication of an FM report in ISC dates back to '89. Dr. A.K. Ghosh worked on that, and they showed that they can solve Euler equations using this mesh-free method and generate very good results. And from then on, a continuous stream of work has been put in, and in about 97 or so we had first 3D computation by my colleague Dr. V. Ramesh, and then various developments took by showing the capability of the method, and then developing higher order method using that, and then moving grids and unsteady problems were also solved using that. And then 3D LSCOM based on entropy variable, which is a very novel way of achieving second order accuracy, was developed. And then viscous applications started from Ajit Mahindra from BARC. And then once this code matured enough, then at that time we started having these big parallel machines being accessible to us. So parallelization of that work was also carried out, and unsteady computations of multiple moving boundaries was tried on. And several theoretical developments were also presented in various international conferences. And you can see here that very large applications started being solved using the LSCO, and the development has continued till now, and it is going on, and we are still working on continuous development of these methods. Okay, so now I will take you through briefly the LSCOM theory. What does it involve? So as the name says, LSCOM, least squares kinetic upwind method. So it involves least squares discretization. That is the mathematical part of it. And then kinetic upwind method. So it is an upwind method. So I will take you through what upwinding is and how it is done. And then that K is the kinetic part. Okay. So I will tell you how this upwinding is very easily achieved using kinetic part. So once you understand these three aspects, you will be able to appreciate LSCOM. So right now you focus on how least squares is useful in evaluating a derivative. If you understand this core concept of how least squares will help you in evaluating derivative, you will understand the remaining parts pretty easily. Okay, so I will take this 1D example. Suppose there is a point P naught. This is a 1D domain which I have represented, and suppose there is a point P naught at which you want to solve the PDE, and you will then define NP naught, which is the collection of points near it, PI. So the collection of PIs is called NP naught, shown by denoted by dashed lines, and you want to evaluate the derivative. You are now given value of f at P naught and PIs. Okay, so at all the points in the domain, you have value of f given to you, and you want to obtain value of derivative. You remember this Euler equation, so Navier-Stokes equation, you will have these derivatives appearing, right? So here we are trying to evaluate derivative for a given function f. So once we are solving those equations, we will have to define this f to be the fluxes which are defined there. So a simple reduction of that is we assume that there is f available to you here. So given an f at points pi which are the neighbors of p naught and f available at p naught, we want to find derivative of f. So what do we do? As I said, it has a neighborhood np naught which are belonging to pi belonging to np naught. Okay, and these points are arbitrary. We don't place any restriction on what kind of neighborhood you want to choose. Just they have to be neighbor. There is no big restriction put. So your point cloud can be anything, and your neighborhood can be accordingly chosen. Okay, and they could be unequally spaced or equally spaced. However, you have full flexibility of defining. That is the strength of the meshless nature. So you should appreciate this point, because once you have a finite volume or a finite difference, you have to either have regularity or you have to define an interface, you have to define a normal surface. Okay, in 1D there will be no normal, but if it is a higher dimension, there will be normals and other things. So what we do, let us expand Fi in Taylor series around P naught. So at any point I near to Pi, near to P naught, where we want to evaluate Fx, let us expand that Fi around P naught. Okay, so what you will have, you will have Fi equal to F naught plus delta Xi Fx plus higher order terms. Okay, simple Taylor series. So you take out that Fi F naught to the left, so you will have Fi minus F naught, which is called delta Fi, equal to delta Xi Fx naught plus delta Xi square Fx, so higher order terms. Okay, so now what you do is you assume that you are going to truncate and approximate your delta Fi up to only first order term. That is, you neglect from this order term. So this is the first term which you will neglect. So this is the error which you will commit. Okay, that is why E is defined here. So you delta Fi, this is the data given to you. This is the approximation, and in this approximation this is the exact thing in which you have approximated up to only here. So difference of this and this will define error. Okay, delta Fi minus delta Xi Fxo. This is the error committed. Okay, and you square this, take the square of sum of that error at all the points. Okay, so at all the points I, we take this square the sum of error, that we call as E. Okay, so you minimize this sum of squares of error with respect to Fx. Okay, this is the ls part of it which comes here. So now you want to find an Fx such that it minimizes the error, that is dou E by dou Fx. Okay, so this E, you take dou E by dou Fx. Okay, once you write that equation, you will get this formula. So if you minimize the norm of E with respect to Fx naught, we will get this first order accurate formula. You will get this. Okay, and there will be some approximation error in this. That is why we have written in the bracket 1, that is first order, because you see this equation we have considered only first order term, only the first order is there. The higher order delta x square is neglected. Okay, so it can be easily proved also that this is only first order accurate. You can just take in the NP naught, just 2 points you take, you can see that Fx naught, this formula with just 2 points on either side will become. This is a central difference formula. Okay. If you have symmetric grid, the first order approximation of LS will look like actually second order. That is the beauty of that, because it will use the symmetry to cancel out on either side. If you take the only on one side, you will see that you will get only the first order thing. You can see that in the next slide. So if we choose only the uh, points on the right side of the point P naught, we can see 3-point stencil first order formula you will get. So if you have a 3-point stencil, the first order formula will be given by this. So if you plug in the earlier approximation of fx, whatever I had given by these 3 points as the connectivity neighbors, you will get fx, which will be this. So this is the same as 3-point approximation of finite difference. Okay, because the least squares reduces to finite difference whenever there is some order, and in the on the uniform stencils, it is also known as generalized finite difference. Generalized because in particular case of structured grids, it reduces to finite difference, but other than that, it has its own property to approximate. So it is more generalized than finite differencing. So when finite differencing is a special case of this, it is called generalized finite difference. Okay, this LS formula is first order, but in typically when we are solving, we need a very accurate result. So we will need at least second order. Minimum is second order when you are dealing with applications. So what can we do? We can include more number of terms when we approximate. Earlier we had included only up to here, delta fi minus delta xi fxo. So now let us include the next term, and now minimize that error with respect to fx naught and fxx naught. So if you do that, you will get two algebraic equations. Dou e by dou fx will give one equation. Dou e by dou fxx will give another equation. So you will get these two equations, and this will form a matrix equation, as you can see, with fx naught and fxx as the vectors, and these as the entries of that vector matrix, and these as the b. Ax equal to b form will come. If you solve that, you will get fx naught second order accuracy with this kind of formula. So leave out the algebra, but what you have to observe here is there is something here in the denominator, and this can become 0. What happens if this becomes 0? If it becomes 0, fx becomes uh, undefined, because it will become infinite, right? So it will become not defined. So it will give wrong result for fx, not because the derivative or function is behaving bad, but because your connectivity is bad. If your connectivity is bad for some points, if you are, because here we are not having any structure, the points can lie in any fashion. For some cases, this can go to 0. If it goes to 0, you will have infinity problem, 1 or 0 problem. Okay. So even though it is an easy method, it is not a good method to achieve second order accuracy like this. This was also followed by Liska and Orkids. They have done some corrections for this also, but this is not a good method as far as applications are concerned, because robustness of method will be lost if you use this formula. So in development of LSCOM, we have followed a totally different method. What we have looked at is defect correction. Defect correction is essentially an implicit method. Here we use the derivative to find the derivative itself. How do we do this? I will explain you here. There is a little bit algebra. I hope you can keep focus on. So in the formula that we used earlier, delta fi, delta xi, whatever we used, fi equal to f naught, that you multiply that by delta xi and take some more I. Then you will get a formula like this for fx naught. Fx naught equal to this formula plus in the higher order it will be like this. Okay. And you can quickly see that this first term which appears is whatever we had derived for. Yeah. Shall I continue?
Yes, sir.
Yeah. So this looks like whatever we had derived for first order approximation. So there is a correction over this first order, which is this term. Okay. So now how do we approximate this to get the second order? Okay. So that second term, which was seen in the previous equation, this term, we can approximate it by So delta xi cube by 2 fxx naught. So what you do, you take 1 delta x inside fxx. We write like this, okay? And if you expand fxx naught in Taylor series, you will get delta xi fxxo equal to fxi minus fxo. There is a difference of first order derivative. So if you plug in this in that equation, you will get fx naught equal to this formula, okay? Just slightly a rearrangement of this will give you tilde fi. You can write this term in bracket can be written like this, okay? Tilde fi equal to this term is written here, and rearrange. So it looks like first order formula with a modified difference here, okay? So fx naught, sorry, I have missed the writing bracket 2 here because this is second order approximation. So the second order approximation of fx looks like first order with a modified difference, and this modified difference involves the fx. So you have to calculate fx, you are depending on fx. So this implicit dependence is there. You can see, first thing you should notice is there is no way that this denominator can go to 0. It is same as what we have derived for first order, okay? Same as that, okay? So you should note that the structure is same as first order. First order has some nice beautiful mathematical properties which are now carried on to its second order approximation also, okay? Only difference is that delta fi is now replaced by modified differences, okay? Because now fx depends upon the fx, there is an implicit dependence. Because of this, we have to do this calculation repeatedly. That is, some inner iterations are required. So, so as I said, it is an implicit nature now. Because to obtain higher order accurate, we need fx. So how do we do? Because to begin with, we will not have these fx, right? So what we do is, we first obtain the first order approximation for fx. That is used in the fx second order approximation formula first, and then you again obtain fxx dash, okay? Now you use this again in the same formula and obtain the fx double tilde. So this is the inner iteration. So you keep doing this for some iterations, you will get a very accurate approximation of fxo to the second order, okay? Okay. So now let us look at the first order approximation of the fx. Uh, there are certain comments in order here. We just took the each point for whatever function value it gave, but we can weight them also. Each point can be assigned some weight, and we can take a weighted sum of their errors. So once we are defining this sum of squares of error, we can take the weighted sum of error. Then we can assign some weights to this to uh, these weights can be used in some way so that you get better approximation. I'll explain you what that is, but here you should know that each error is given some weight. So if you derive from this formula of E, you will again get except the same formula except that WI's weights appear here, okay? And this is the truncation error which you will get. Here also weights are ignored, okay? So what does that do? So you can put the weight such that it is the it gives less weight to the points which are further away from the point at which we are evaluating than the points which are closer. So derivative is a local property, right? So the points which are closer to it should have higher weightage. And points which are farther should have less effect on this estimation. We can implement that by taking the inverse distance of the weights there. That is what is done here. If you take that way, you will get the effect of more effect of points nearby and less effect of points which are farther by. There are other methods also to choose these weights, uh, but let us not go into that. But look at now the multidimensional formula. This was done for 1D now. So how do we do for 2D? So for 2D, other than the x derivative, y derivative also gets added, and this your term error becomes delta fi, delta xi fxo minus delta yi fyo. Okay. Here we have included weight right from the beginning. So you minimize the square of sum of error e, with respect to fx naught and fy naught. Okay. So if you minimize like that, so this is the point P, x naught, y naught, and this is its connectivity, and all these are its neighboring points Pi. So you the define E for all the points around here with some weights, and we define it this Taylor series. NP naught is the connectivity here, and you want to evaluate fx naught, fy naught. So minimize this C with respect to fx naught and fy naught. So you will obtain two equations like this, where fx naught and fy naught have to be solved for. So we can write that in a matrix form. This particular thing has been written in matrix form. Fx naught, fy naught are column vectors here. This is the column vector here, and these four coefficients appear as matrix A. So it is Ax equal to B form. Okay, and you can see that. You should know that this is a 2 by 2 symmetric matrix. Symmetric matrices have nice properties, right? So we have got a matrix which is symmetric, which is a big relief when you're dealing with numerical methods. Okay, so numerical, the nice properties of that can be used. So if you solve that Ax equal to B, you will get this formula fx fy. If you solve those two equations, you will get this formula. So this formula gives you fx, and this formula gives you fy, and this is the determinant. This is the determinant of this, and you should know that this is the, you can easily recognize this, that it is a Cauchy-Schwarz inequality. It will be zero only if delta x and delta y are related in some ratio, that is they are along some straight line. Since we are dealing with 2D, we expect that all the points will not be on the same line. If they are there, it will become indeterminate, but because we are dealing with 2D, the points will be distributed around, and we will generally not encounter this problem. However, we have to take care when we choose connectivity that they should not lie on a straight line. So you can see this. I had talked about invariance, right? So let us see whether this numerical method has invariance to it. That is the rotational invariance. So we have defined error like this, EI. Okay, and let us take a rotated frame x prime, y prime, and see what happens. Okay, so if you write that equation in this x prime, y prime rotated frame, E equal to derive in this rotated frame, the rest of derivation is same, and you will again get the same formula which you got in xy frame. So the formula in x prime, y prime frame and formula in xy frame are same. That is, they are not changing. They are invariant under those frames. Why is this important? This is important because you see here, this is happening also because of delta xi fxu, delta yi fyu. This is what appears in Taylor series here. Okay, and this is carried down to its numerical method, to its approximation also. Now this exact fx is replaced by accurate, exact fx is replaced by approximate fx, denoted by 1 in bracket. Okay, and that has imbibed the invariance of fx and fy to its numerical approximation also. Okay, so the numerical method has inherited the rotational invariance that is there. Okay, so this is a good property of the scheme. Why this is important will be seen when we derive Boltzmann equation also, where v1 and v2 are velocities and fx and fy are approximations of the Boltzmann function, Maxwellian function there. So that invariance will be there in the kinetic level, and when we take mapping, it moves on to Euler level. So the scheme at Euler level, first order, will be shown that it is invariant. So what I had shown, that there is no preferred direction of propagation, will be satisfied by numerical scheme. So this particular aspect was used in developing LS comb. LS comb was developed to include invariance, and that method was called as Kumari. That was my research work actually. And again, few comments in order, because I said x prime, y prime, and xy, the formula doesn't change for the least squares approximation. It gives us some very nice properties. One is at the boundaries where the frames can be defined locally, the formula don't change. So if you change the frame locally at the boundaries to handle the geometries of realistic bodies, your formula doesn't change. You can apply the same formula by just rotated coordinate frame. Like flow tangency that is implemented in Euler flows, it will be very easy to implement here. Okay. Okay, and suppose even in the free stream, if you want to do some streamline upwinding, that is, use upwinding along streamline direction and full stencil, that is, do not worry about the upwind property in the normal direction, you can easily implement using the this scheme without much problem because the scheme remains the same in whichever frame you use. Such things are not easy to do in finite volume methods and finite difference methods. You have to do a lot of jugglery to get to that. So another aspect which I want to express here is weights which I told have been introduced can also be chosen such that the second 2D formula becomes like 1D. I had explained to you that 1D has some nice formulae that its numerator does not become 0 at all. So because that symmetric matrix is there in the 2D, we can choose weights such that a total diagonal dominance appears and fx and fy become decoupled. Once they become decoupled, they will become like 1D formulae. Even though delta fi here is 2D defined in 2D, the formula will become like 1D. So you can choose weights such like that. There is a lot of detail to this, but for you, I want you to appreciate that there are various ways of choosing this weight, which can lead to very good numerical properties. Okay, and similar to what we did in 1D, similar thing can be done in 2D using defect correction to obtain higher order approximation for the fx naught and fy naught. Same as we did, we will include the higher order terms fxx, fxy, and fyy, and minimizing fx not fy, and if these additional terms appear here compared to first order formula. And here for fxx, fyo, these for these we substitute these approximation delta fxi and delta fxi. These terms are so if we look at fxi equal to fxxo, fxy, if we put them in this has to be slightly different. Fxi and fyi should have been there here. So if you delta fxi and delta fyi, you rewrite, you can get this rewritten in terms of delta fx. You can see fxxo, delta xfy, full fi. Similarly, delta yi can replace here. So like what happened in 1D, it same thing happens. Just that AW matrix fx fy the AX part and B gets modified with just tilde fi here. Okay, and you get second order accurate formula. Same as what we got in 1D with defect correction, we get in 2D also. So since you have seen 1D and 2D, there is not much of difference. The methodology followed is very same. You can easily very well think that the formula will remain the same in 3D also. You can of course try to derive and find yourself. The formula remains the same, only the matrix gets changed for 3D. The remains structure remains the same, only additional z variable appears and you will get the same form. Okay, and of course because tilde fi depend on the fx, we will need inner iterations to achieve higher order accuracy. So now that I have told you how to evaluate a derivative using least squares method, a first part in LSCOM, I will now take you to the second parts, the kinetic part and the upwind part. Kinetic part appears because it is we are using kinetic flux vector splitting method here, and upwind because the Euler equations have to satisfy upwinding property. Okay. So first I will show you what upwinding is, and then once I explain that, I will use that in the kinetic framework to show you KFVS derivation, which will be used in LSCOM. Okay. So you take a typical wave equation ut plus c ux equal to 0. Some quantity u is transported okay, with speed c. You can derive if c is a constant number or very constant thing. You can derive that the solution at n plus 1th level will depend at nth level at x minus c delta t. That is, if solution at an next time level is required, it will depend on the previous time level at a point which is x minus c delta t. Okay, so you can easily see that if c is the velocity, x minus c delta t will lie the upwind of that. That is, c, if velocity is moving from left to right, this is upwind point. So you can see that x minus c delta t is upwind. That is why it is called upwind. Wind is this direction, upwind is this direction. So we are choosing points in the upwind direction. Okay. So information travels from this point to this point at the next time level. Okay. And if velocity is negative, this will become upwind point. So this has to be respected when we want to have a numerical scheme. This is the exact solution. If we have a numerical scheme, it should mimic this form. Okay. So you consider this state upwind, as I explained. It's called the numerical scheme satisfying above property is called upwind scheme. So you have n plus 1 n lambda uj minus 1 if lambda is positive. So you can write like this, provided lambda is greater than 0. But if lambda is less than 0, what do we do? So there is a splitting offered by Courant, Isaacson and Rees, CIR it is called. If you write lambda or c in some particular way, the scheme naturally respects. That is, you write c by splitting it into positive and negative part. So if c is positive, this will be positive and this will become 0. If c is negative, this will become 0 and this will be the c, negative c. So by writing like this, c will take only positive or negative values, which you can split like that. So this will become positive part, this will become negative part. Once the velocity is positive, you know that you have to use the velocity is positive means left to right or right to left. So you have to use backward differencing and forward differencing. I think there's slightly written wrongly here. This should be backward difference. This should be forward difference. Okay, just a small mistake here. This is forward difference. This is forward difference because velocity is negative. Negative is coming from right to left, so you have to use the points on the left. So on the right, that is uj plus 1. So you write like that, so the numerical scheme you will obtain will properly respect, because this will become 0 if velocity is negative. This will become 0 if velocity is positive. So this obviously satisfies upwinding property whenever c is greater than or less than 0. You don't have to worry. The scheme naturally chooses which of these uj minus 1 or uj plus 1 minus uj, which one to use. So it will naturally choose based on this splitting. This has been used for kinetic flux vector splitting. So in the kinetic flux vector splitting, this is based on the kinetic schemes. Here we derive the Euler equation starting from the Boltzmann equation. Boltzmann equation is a kinetic representation of gases and there is a certain thing called velocity distribution. If you take Maxwellian, you will get Euler equation. If you take Chapman and Skoog, you will get upwind scheme. If you have to take the moments of those schemes, and you will get Euler equation. So kinetic schemes use the property of kinetic representation of gases, which when taken moment will give you uh, equations at Euler level, that is at the continuity level. Okay. So this is the Boltzmann equation without the collision term. F is the distribution function here. So that distribution function, this looks like what you saw just now, right? The wave equation. So this represents the same properties that wave equation has. Okay. Only thing is F also includes V. F is not constant here, it is varying. So you will not have exact solutions available immediately, but uh, properties will be similar. So these are the definitions of the F, Maxwellian velocity, and all these density, the beta, and gas constant, absolute temperature, fluid velocities. are defined. These are for fluid velocity is u, and this particle velocity. This is the mean velocity. This is the particle velocity. That is molecular level. Okay, these are internal energy representations and degree of freedom. You don't go get into details of these things. Suffice it to say that this is a Boltzmann equation where if we take F to be Maxwellian, its moment will lead to this will lead to Euler equations if we do some operation on it. Okay, from kinetic representation to Euler representation is possible. So you take the moment of that equation where the moments are defined like this. V is the velocity of the molecules. Moment means they are just these integrals. So you take this u, so you take this f and take moments with this. If you take with 1, you will get rho. If you take with, if you integrate this with v, you will get rho u. You take with I plus v square by 2, you will get energy, this integral. Similarly, you will get fluxes like this if you take this. This is just integral. It's called taking moments. So why is that now? The same Boltzmann equation, if I split this V using Courant splitting into plus and minus part and then take psi moments, I am going to get fluxes which have contribution only from either plus part or minus part. So this F, we saw that this F moment leads to this G, right? So this G now is modified because of plus and minus separate contribution. So we will get G plus and G minus. So the flux gets split into plus and minus because of the splitting. So we will get this KFPS split Euler equations. We take the moments like this, we get this Euler equations. Okay, this is the same moment vector. So what do? We do all theoretical manipulations at Boltzmann level and then take the moments, suitable moments, we get to the Euler level. So these are the split fluxes which are written. Once you are split into plus and minus, these are the suitable integral limits. You can see if you take from minus infinity to plus infinity, because of this, you will get only the plus contribution, you will get only the minus contribution. Okay, and full flux equal to plus and minus. This is the consistency. This is the F, and this represents plus and minus part. This is the velocity V. So just to give you easy to understand of the easily understandable way of this KFVS, if we take the Euler equations written in using KFVS, dou u by dou t plus flux and minus flux. Plus flux, you have to do backward difference, G minus 1 and this. And minus flux, you have to do forward difference, plus and minus. So if you do this, it's a very consistent approximation which represents upwinding. Pretty simple to understand that, right? So this derivative, space derivative is done like that. Same thing is done in finite volumes. Let's not get into the algebra of this, but it is the same thing essentially, defined at the interface of fluxes. So now let us go to the LS Kum aspect of it. So LS discretization of CSIR split Boltzmann equation. So this is the KFPS split Euler equation, and this is the derivative of G plus and this is the derivative of G minus. Okay, and now let us define the point P naught and its neighborhood NP naught at which we want to solve this equation. Okay, and now that there is a G plus and G minus, we define substances. For G plus, we know that only points to the left should affect. For G minus, we know that only points to the right should affect. So we define N1 to be points which are lying to the left, N2 be the point which are lying to the right. Okay. And now approximate this dou G plus by dou X. So G plus is now like F, what you were studying when I was telling about least squares approximation of derivatives. So F there is now G plus. Here the F is G minus. You use that. So least squares approximation of this Gx plus will be delta xi, delta fi, delta xi square. So that formula is here. So whatever you have put here, it comes here. Okay. So here earlier you used to say delta fi, delta xi square was the formula. Okay. Now instead of the delta fi, you are now getting g delta gx plus delta gx minus. If you do that, you get this derivatives. I hope it is fairly straightforward for you to understand. Okay. So this least squares approximation will be given by that. And if you put the least square approximation here and use a simple state update, forward time difference, un plus 1 minus equal to u naught, this is un plus 1 minus un by delta t. If you put here, you will get a state update formula for un plus 1 equal to un delta t and delta x delta t delta t. It is representing the least squares LSCOM. So this is the LSCOM state update for 1D problem. Okay. So just you have to understand here a simple fact that f is now gx plus and gx minus here. You have to evaluate it twice. Similarly, in 2D, you will have u naught plus n1 u naught minus delta t, the plus x derivative with respect to x flux derivative with respect to x minus gx minus with x, and then gy plus and gy minus derivative with respect to y, defined on suitable stencils. So for x, you have to define left, right. For y, you have to define top and down for upwinding. And the formula for that remains the same as what you saw in the when the function was f. This is the f for x derivative formula. This is y derivative formula. So you have to do this for gx plus and gx minus twice, and you have to do gy plus and gy minus twice. So you will get the state update. So this is called upwinding by stencil division. That is, you are dividing the stencil np naught into upwind stencil. So it is called stencil division. Okay. So some points to note here. LSCOM based state update uses the KFES fluxes. It is clear to you now, I suppose. And stencil splitting is used for achieving upwinding. Okay. And velocity splitting is done at Boltzmann level, and then we pass on to the Euler level to get the split Boltzmann equation. Here the state update is first order. You can use any other state update because once you discretize the space derivative, it becomes ODE. So you can use any time order scheme like RK2, RK4 to solve that ODE. The PDE has become ODE. You can solve that ODE by any method. And second order accuracy can be achieved by what I had described as defect correction method, that is defining tilde Fi. Okay. So same thing you can see here. Whatever was the earlier F now becomes delta Gi. Okay. And those becomes tilde Gi here. Same thing. So and this becomes the second order in space for plus and minus. So you have to do some inner iterations to accurate or obtain accurate solutions. Okay. The modified differences in 2D are similarly given. It is same as that, and you can use RK2, RK4 for 2D also. So this in nutshell is the LSCOM's heart. If you understand this aspect, you can code the LSCOM solver also. This is the QLSCOM method. I will skip this part. I'm not going to go in detail with this part. But what I want to impress upon here is these are called Q variables. Like you are using the U variables, the Clunzard variables, you can also represent Euler equations in Q variables, entropy variables. So there is a one-to-one correspondence between them. So why Q method has been brought here is once you are doing the defect correction kind of thing or reconstruction kind of thing, when you might have heard that in finite volume also. Once you do that, the Maxwellian that you get may not be the reconstructed max flux function that you get need not be Maxwellian. Just to achieve that, Q variables are used because the linear combination of Q variables is again a Maxwellian. So when you're doing reconstruction, you use linear combination. So that linear combination again has to be Maxwellian. So to ensure that Q variables are used, I would say I would suffice it to just that, not going into too many details. So I'll skip these few slides here. And these are the boundary conditions which are defined in the kinetic characteristic boundary condition. These boundary conditions are very unique to the kinetic schemes. because just using the specular reflection model, that is an incident particle on the body will reflect with equal velocity but in the opposite direction and will not have any tangential velocity. This is the specular reflection model. So if you use this, you can very well derive a boundary condition for Euler equation which will have a state update equation. So you split the Maxwellian into incident part and reflected part, and you can easily get the uh, flux equation, state update equation, which represent the solid wall boundaries for Euler equation, where these fluxes have been defined with these moments. Okay. So what is interesting for you to observe here is you use a reflection model for the velocity incidences on the solid boundary, and then take the suitable moments. You will obtain a boundary condition at the Euler level. That's all you need to appreciate in this. Similarly, in the outer boundary condition, you can split the information. At the outer boundary, the outside the domain, the free stream is already defined. Inside, the flow field is defined by whatever data is there on the inside. If you respect these 2 points, you can split the Maxwellian into incident part which is outside and part which is inside. So outside part is known, inside part can be derived from the data that is inside. So if you use this approximation, F inside, F inside and outside, if you define, one is free stream, one is inside. So if you do this, you will obtain the state update equation. What I want to appreciate in whole of these two boundary condition is it results into a state update equation which is same as what you have in the inner points inside the flow domain. That is, the state update at the boundary and state update at the points inside the domain are similar. This gives enormous advantage when you are coding the LS scheme in order to use the scheme very effectively. Your boundary need not be handled in a very special way because the scheme update will be very similar. That's all I want you to update, appreciate in these two boundary conditions. Okay. So I will finish my comments about LS cum on that.